Before I start this video, let me take 30 seconds to tell you something about Exergic. Exergic is India's most trusted and most experienced institute for online GATE preparation. I am Chandresh Mahajan, founder and chief educator at Exergic. I am an All India rank 37 in GATE Mechanical Engineering, an ex-Indian Oil officer having 7+ years of teaching experience as of now. These are the GATE 2021 Mechanical Engineering toppers from Exergic. You can find their preparation strategy on Exergic's website. To know more about our GATE courses, you can visit our website or contact us on these details. Also, you can download Exergic GATE preparation app from Google Play Store. The link is available in the description of video. So as we discussed in the previous lecture, that if we have a shaft of diameter d and we apply a torque T at its ends, the maximum shear stress is going to appear on the farthest point from the center, or in other words, on this periphery, on the circumference of the cross section, right or not? And the value of maximum shear stress which will be acting there can be determined using this expression 16T divided by pi d cube, right or not? We also know that the variation of shear stress is linear. We also know, we have discussed that the variation of shear stress is going to be linear like this, right? Obviously maximum value at farthermost point. The question that I want to ask you is that can I use this expression for any other point also? What I mean to say that if in place of d I put d by 2, means a point which is lying on a circle of d by 2, on a circle of diameter d by 2, or in other words a point which is lying at a radius of r by 2. Both the things are same, na? If a point is lying at a distance of r by 2 from the center, or in other words the point is lying on a circle on a periphery of diameter capital D by 2, basically half of the maximum diameter or half of the maximum radius, right? So can I say that if I replace D by 2, if I put D by 2 here in place of D, then this value will automatically get changed to the correct value of shear stress? No, it will not work like that. Why? Because obviously if we are choosing a point which is at a distance of r by 2, in place of r, so how much will be the new value of shear stress? Tau max by 2. We all know that tau is going to vary linearly, so we cannot have tau max by 2 if we put d is equal to d by 2. You can put the value and you can check that the value that you will get will not be equal to 8t by pi d cube, right or not? Because if that value is getting half of the maximum value, so in place of 16t by pi d cube, upon putting d by 2, I should get 8t by pi d cube, half of the maximum value, which we already know. But we are not going to get that value. So clearly something is wrong somewhere. And let me tell you what is wrong. It's a conceptual learning which many aspirants do not know about. If you ask any general aspirant that can you apply this expression at any point, either he will say yes, just replace d in place of d by 2, or he will say no, this expression is only for determining the maximum value of torque. But that's also not true. You can use this expression to determine the torque at any point, but you have to modify this value as well, and then you will be able to get the expression of torque anywhere on this cross section. And that is what we are going to discuss in this lecture. And with this discussion that how we can find out the variation of torque, how this expression can be modified, we are also going to understand 2-3 more concepts. So this lecture is going to be extremely important to understand. Look, generally if we have, let me relate this situation with the situation of a normal force acting. Okay, so suppose on this rod, now this is not a shaft are used to resist torsion. We are not applying torsion on this. We are applying a tension force. So it's a rod now. On a rod, if we apply a tensile force, tensile load P, okay, how much is going to be the value of stress? Stress is equal to P by A, where A is equal to pi by 4 D square, right or not? In this expression, if I ask you that if in place of complete area, I am only selecting this area, suppose, tell me that if I select an area which is not the complete area but only some part of the area, then can I use the same expression to find out the stress? Yes, I can use that, because I will be changing the area also, or in other words the diameter also of the inner rod, of the inner core, but at the same time I need to change the value of P also, because whenever such load is being applied, entire material of the cross section is resisting the load. Very basics, we have understood that already. But if we are only trying to find out how much is going to be the stress or how much will be the load resisted by some area, then obviously load is going to change. The load P was being resisted by the entire area of this cross section, but if I only want to analyze a small part of the area, I need to modify the P load as well. That load I have to consider, which is being resisted by this material, the material that I am going to consider here in the expression of area, right or not? In a very similar way, if in this expression of torque, I want to find out how much is going to be the torque resisted, right? How much is going to be the torque resisted at a certain point by using this expression, then not only this expression, this D needs to be modified, but the torque resisted by that area only needs to be considered. That also needs to be modified. Then you are going to get the same answer in this discussion. By the end of this discussion, we are not only going to prove this, that this expression you can apply anywhere. You have to select appropriate value of torque and appropriate value of diameter, but also at the same time you will see that how torque actually varies across the cross section, what is the general expression of that, and it's very important that you remember it because it is used in some questions, in some discussions. So let us start that discussion. So this concept of torque distribution we are going to understand from the help of an example. Basically, whenever we are applying a torque to any given shaft, entire torque will not be resisted by only the outer periphery. Obviously, the torque, any such disturbance, any such load is resisted by the entire cross section, just like in case of tensile load. Only difference is that in case of tensile load, stress value does not change. If you apply a load P, stress is uniform throughout, P by A, right? So it's easier to find it out in that situation because stress is same throughout, which is not the story in case of torsion. In case of torsion, stress, which is the shear stress, is varying continuously. So you cannot directly find out and directly conclude that torque variation will also be uniform. Just like load variation will be uniform in case of tension, torque variation is not going to be uniform in the case of torsion because as we have already derived it, shear stress variation is not uniform, it changes, it varies, right? So we are going to discuss that using this example. Let's start the discussion. A solid shaft of radius r is subjected to a torque T. So as you can see here, there is a solid shaft. Don't look at this line here, just look at this entire cross section, right? Solid shaft means a shaft which is not hollow, okay? So a solid shaft of torque T is subjected to a torque T. Determine the fraction of torque that is resisted by the material contained within the outer core of the shaft. So it's asking that entire torque obviously is not going to be resisted by a small fraction of material, rather complete material is going to resist the torque. But that distribution, we don't know yet how it's going to be distributed, how torque is going to be distributed. So it's asking you that tell me how much torque will be distributed by the outer core of the shaft. What is outer core of the shaft? What is the dimension of outer core of the shaft? Outer core of the shaft has inner radius of r by 2 and outer radius r. This is what I have drawn here. This circle is at a radius of r by 2. and this outer circle is at a distance of r. So obviously outer core is this one, which is confined between inner radius of small r by 2 and outer radius of r. So you have to tell how much will be the fraction of torque, fraction of total torque that will be resisted by the outer core. Will it be T by 4? Will it be T by 5, T by 6, or how much? I am not giving you options, just giving you how the answer is going to look like. So as you can see here that this shaded portion here is having an inner radius of r by 2 and outer radius of r, right? And this is the area which I want to know that how much torque it will resist. I will go by performing the integration here, right? Because shear stress is varying, diameter is varying, so integration is the best way forward. What I will do that I will consider any small area dA, for example this one, right? It's a small area dA, very small elemental area, right? Which I have considered, which is almost like a point. It's very small. You can call it to be a point, you can call it to be a small area dA, right? Again, nothing new here. We have been doing this integration and considering small area in earlier lessons, earlier lectures as well. So that small area dA I will look at, and I will see how much torque is being resisted by that small area only. And then I will integrate it for the entire area. I will take all the small area on this outer core and I will add their torques together by performing integration to get the final expression of torque. Now obviously when I move forward, it makes sense to select those areas first which are at the same distance from the center, right? Because while finding out entire torque, R value will be same for them, right? So it's easier and a logical way to start with. So as you can see here that I have considered a thin ring. It's a very thin ring having thickness or radial thickness as d rho, very small. It is situated at a distance of rho, as you can see here. So in the entire outer core, I have considered a very small ring, thin ring, very small, at a distance of rho, having a thickness of d rho. Firstly, I will find out how much is going to be the torque resisted by this elemental ring, by this thin ring. And then I will integrate it from inner value r by 2 to capital value of r. That will give me my final expression of torque. So how can I first find out the torque resisted by the thin elemental ring? This one, the highlighted one from the yellow color which I have shown. This ring, as I told you, is situated at a distance of rho. This rho value is a variable. Minimum value of rho is r by 2, maximum value of rho is r, and this thin ring is having a thickness of d rho, right? So for that I will consider any small area dA on this ring, right? Obviously that is also at a distance of rho. This is also at a distance of rho. How much will be the torque resisted by that? This small area dA. So what is this expression giving me? This expression is giving me the small force dF that will be resisted by this small area, right? So dF force. Shear stress, we know the direction of shear stress. In such a situation, we know how shear stress varies, right? So that same direction is going to be for force as well. So that's why the force dF that will be resisted by this small area is given by the multiplication of shear stress with the area. Again, the very basics of stress, right? Now, what can we do? Since we are interested in finding out the torque, so we need to multiply this with the distance. It is situated at a distance of rho, since this entire ring is at a distance of rho. So we will be writing rho here. This is only giving me the torque resisted by this small area. But if I consider another such area, right, same thing is going to get repeated. If I consider another such area which is also dA, that is also going to resist the same shear stress. The value of shear stress for entire ring will be same, because entire ring is situated at a same distance of rho from the center. So the value of shear stress for all the small areas dA on the elemental ring will be same. Tau will also be same. So tau is going to appear again, multiplied by dA, which is the area, multiplied by the distance, which is rho. And same thing will continue throughout. To differentiate them together, to differentiate the different areas, let us do one small variation, only to differentiate the area. It will not matter in the long run. Let's say this is dA1 and let's say this is dA2. Okay, all the areas are very small, almost the same, but just to differentiate these expressions together, let's say this is dA1, this is dA2, and so on and so forth. We will be able to write all the expression for all the points, right, on this ring, and all of them are going to perform this torque. They are going to apply this torque in the same direction about the center. So we all know that to find out the net torque which is going to be resisted by the ring, we can add all of them together, right? This is something which we have covered already in the basics of engineering mechanics, right? Since this is trying to rotate it in this direction, so the direction of the vector, torque vector, thumb, is moving out of the plane. For this also, for this small area also, it is moving out of the plane. For this small area also, curl your fingers along the direction of force. This is going to be, thumb is going to give you the direction of torque. Since all of them are trying to apply the force in the same sense, right? So the direction of thumb torque will be same for all of them. So if I add all that together, vectors in the same direction can be added together. Na? Torque is a vector, but I am able to write it like this because they are in the same direction. All of them are trying to rotate in the same sense. So I am adding all those together. That's why this is the expression. This is the expression that we are having. In this expression, tau and rho, these two values are common. So we will take them out. We will be writing tau rho. What we will be having other than them? dA1 plus dA2 plus dA3 plus up to dAn. Right or not? What is this? If I add all the areas on this ring, all the small areas on the ring and their torque, this is going to give me the entire area of the ring. So ultimately this is equal to tau rho multiplied by area of the ring, right? And how much is going to be the area of the ring? How much is going to be the area of this ring? This is again something that we already know. If we have a thin ring, in that situation, don't apply the expression of outer circle minus inner circle. To find out the area of ring, don't do that outer circle minus inner circle will give me this area, because a ring, thin ring, elemental ring is so thin, it's almost a line, it's like a line. Obviously, if I am trying to explain something, I will show it bigger and thicker so that you can see it. But if we perform such integration, really this is the thin ring, even smaller than this, make this even smaller. So it's nothing but just a line, right? So if I want to do that, I can find out this length by opening it up, right? If this yellow ribbon, yellow ring, I cut it and I open it, what shape will I get? I will get this shape, the shape of a rectangle. The length of this rectangle is equal to the circumference. If I cut it and if I open it, this length, this circumference is going to become the length, which is 2 pi rho, right? And how much is its thickness? Thickness is d rho. So how much will be the area? This area, multiplication of both of them. 2 pi rho multiplied by d rho is going to give us the area of thin ring. Please note that this is not true only for this derivation. This type of analysis, when parameters are having same value from the center, this type of analysis you will see everywhere. We are going to perform this in machine design. We are going to perform this in theory of machine. We are going to perform this in fluid mechanics. We will be seeing pipe flow in fluid mechanics, Hagen-Poiseuille flow, viscous flows. So there we are going to perform such integrations where we will consider the parameter having same value from the center. We will consider that ring only, the same expression of area, similar analysis we are going to do. So this is something which is very basic, which will be used entirely across different subjects. So the area is 2 pi rho d rho, right? So if I multiply that, if I put that value of area here, what am I going to get? dt. This is the expression of dt. Why dt? Why not complete torque? Because even after performing and adding all of them, we are getting the torque which is resisted by this elemental ring only. We are not getting the entire torque from here to there. We are only getting the torque resisted by the ring. So it's still dt, right or not? So dt is equal to tau rho. Area was 2 pi rho d rho. So if I multiply it, what I will get? 2 pi tau rho square d rho. Right or not? Upon performing the multiplication and putting the value of area of ring, this is the expression of dt that I am going to get. It's not over yet. It is not over yet. In place of torque, I can represent torque in terms of tau max, right? In terms of tau max. How? Because I know that the variation of torque is linear like this, right? So the value of torque tau at the distance of rho, right? This value of torque tau is not the maximum value. It is the value of torque at a distance of rho, right? So if I want to find out, and if I want to write tau max, I want to replace tau in terms of tau max, I can use the basics of this torque variation. That if I look at the variation, then tau by rho is equal to tau max divided by r, right? This is tau max at a distance of r. Since the slope is same, you can say the variation is linear. So this is something that I can write, right? And I have done that already. Tau by rho is equal to tau max by r. This is tau max, which is at a distance of r, and this is tau at any distance of rho, which is between r by 2 and r, right? And this, if I put rho on the other side, I will get tau by r. So this is the expression of tau that I will get. And if I put this expression of torque back into the expression of dt, this is the expression of dt, na? 2 pi tau rho square, same expression is written here, 2 pi tau rho square. So in place of tau, if I put this expression, what I will be getting? Tau by r will be coming, and this tau max will also be coming here. So basically this is what I have written in place of tau. Okay, it is not over yet. This is again not the final expression. In place of tau max, what I can write? I already know that tau max is equal to 16t by pi d cube, right? Generally, the discussion that we do, the questions that we get, generally I am telling you, not always, the data given is of diameter, not of radius. The value asked is of diameter, not of radius. Generally I am saying, okay, you have to carefully read the question. What question has given you, diameter or radius? You have to carefully check what question is asking, diameter or radius. These are very possible silly mistakes that students do. But generally, the expressions that we remember are in terms of diameter, because at the majority of the places, diameter is discussed in mechanical engineering. So this is the expression that we generally know and remember. But this question has given you r by 2 and r in the question, right? So let's convert that, right or not? If we put 2r in place of d, it will become 8r cube, and ultimately 16 will be crossed. So we'll get 2t by pi r cube, right? So tau max in terms of r is 2t divided by pi r cube. So that value we are going to put here, as I have shown here, tau max expression. And if we put it back here, then this is the expression that we will get. Now pi and pi will cancel out. 2 multiplied by 2 will become 4. T will come here, rho multiplied by rho square will become rho cube, dt will stay here, and denominator will have r to the power 4. Cube is present and additional r is also there. So this is the expression of torque dt, which is telling you how torque is going to be defined for any such elemental ring. This is the expression that you have to remember, that you have to write down in your notes. Theoretical question can be asked upon the variation of torque based upon this expression. And if you look at this question, right, basically I am not solving this question, I am explaining this topic to you, right, which can be done through numerical example only. It's a numerical example, right? But it's not necessary that question will always give you the same points that this question gave us, that how much will be the outer core. Question can ask you anything. Question can ask you this for radius of r by 3 also. It can ask you something else also, that how much will be the distance of the point where 50% torque will get resisted. This is another way to ask the same question. In fact, this is the next question that we are going to discuss. After this question, next example we are going to discuss, which will be the same example that I just told you. So there are multiple ways in which this expression can be used depending upon what is the question, what is the data, whether it's a theoretical question or a numerical question. For this question, what we need to do? We need to find out the torque resisted by the outer core. So this value of d rho is going to vary from r by 2 up to r. So in order to find out the net torque, we are going to integrate this expression from r by 2 up to r. Right? Let us do that here. So as you can see here, that the net torque which is being applied, some part of that torque is going to be resisted by the inner core, some part of that will be resisted by the outer core. If you add both of them together, you are going to get the net torque which is being resisted, right? Net torque, some part outer will resist, some part inner will resist. Here, right now, we are interested in finding out TO value. Why? Because the discussion that we are doing, that asked us to find out how much will be the outer torque in terms of the total torque fraction, right? That's why what we are going to do, we are going to integrate this expression of dt to find out the outer core's torque resisted, which will be given by integrating it from r by 2 up to r. So from r by 2 to r, we perform this integration. You put the expression 4t r to the power 4 r constant, right? Please note, r here is not the general radius, any radius. It's specifically the maximum radius, which is a constant value. So 4t by r to the power 4 will come out of the integration. Rho cube will become rho to the power 4 by 4. 4 and 4 will cancel. You will get t by r to the power 4 and rho to the power 4 from r by 2 to r. Put the value, simplify it. This is the expression that you will get. It's a very interesting expression. And please note, there are 2-3 things that I want to discuss right now. Okay. Not only finding out the value of TO, but some other point that I started earlier. I started this lecture with one point, whether we can use the expression of tau is equal to 16t by pi d cube. Remember? So we are also coming to that. So the value of TO is equal to 15 by 16 times of t. If I convert that into percentage, I think it's 93.75%, almost 94%. What is it telling you? You are applying a torque T. Almost 94% of that torque is being resisted by this outer core only. So the inner core is resisting only about 6% of the torque applied. So if you want to save some material, you can make this as a hollow shaft and still this will be able to resist almost 94% of the torque as a solid shaft. Why would you want to make it a hollow shaft? Why? Because whenever such shafts you are making, who are making these shafts? Industries are making this shaft. Saints and sadhu sannyasi are not making this shaft. Why am I saying this? Because profit is always there. If industries are making it, profit will always be a point to consider. If you can make a shaft which can resist almost 94% of the torque by saving a lot of material, it is definitely good for the industry to sustain, to profit, to grow. And that's what the society is expecting from you as an engineer, that you should be able to make such designs which are usable, strong, at the same time they are saving material, they are good for the society. So here, by not using a solid shaft, by using a hollow shaft, you can not only save material, shaft will be economical, but also you are able to resist almost 94% of the torque which you were able to do earlier when it was solid. And recall the last lecture. In the last lecture, we have already discussed about solid shaft versus hollow shaft. We already know that if you want to have the same material, if you don't want to save the material, definitely it would be wiser, depending upon the situation, to place it farther from the center, right? Rather than having a solid one. Again, there are ifs and buts and constraint. When I say this, it all depends upon the case, as we have already discussed in the previous lecture. So this is the beauty of solid shaft or hollow shaft. Definitely it can be asked as a direct question. Question is expecting that you do all this analysis at your end. Question can ask you how much percentage, just like this question, will be of torque will the shaft be able to resist if inner core is removed, inner core of R/2 is removed. Same analysis you have to do. Better learn this value, 93.75, almost 94% of the torque. Getting it? Coming back to the original discussion. Question was, find out the fraction of total torque that will be resisted by the outer core. That is 15 by 16. How much will be the torque resisted by the inner core? 1 by 16, right? 1 by 16 plus 15 by 16 of T will give you total torque T, right? So inner core is resisting a torque of T by 16. Now let us come back to the initial discussion that we were doing in the very first point, that if we have a solid shaft, consider this to be a solid shaft of radius R, and on that shaft we are applying a torque T. To find out the maximum value of torque, I am using 16T by pi d cube, or in terms of radius, what can I write? It's 2T divided by pi r cube, right? But if I want to find out the value of torque at any point on the cross section, can I use the same expression? This is the initial discussion that we were having, and I told you yes, we can use this, but we also need to modify the value of torque. Not only the value of radius, but also the value of torque. Earlier we were not knowing how torque is going to change, but now we know it. Especially for this case of R/2, we know it, that how torque is going to change. So let's have a look at this case, that if in this situation, if we consider only the inner core, only this part. Suppose I am asking you that find out the value of shear stress at a distance of R/2 from the center. So what can you do? Firstly, what you can do, that find out the value of tau max, okay? And to find out this value of torque, let's say it is tau dash, which is at a distance of R/2, divide it with 2. Why? Because we know that the shear stress variation is linear. So at a distance of R/2, torque will be half of this. So tau dash will be T by pi r cube, right? This is one way of doing it. Obviously, easier way if question is only asking you shear stress. But if you want to use this expression directly without finding out the shear stress distribution, directly by the formula you want to get the answer, right now you can do it. The value of tau dash will be equal to 16 Ti divided by pi r/2 cube. How? I have modified the value of R as R/2. The value of torque also has been modified as Ti. Why have I done that? Because to find out how much will be the torque at that point, I want to know, I should be knowing how much will be the torque resisted up to that point. Only that torque is going to come here. Just like in this expression, total torque we are considering. Why? Because to find out the value of tau max at this point, I need to know how much will be the total torque that will be resisted by the area from the center up to that point. That entire area, how much torque it will resist? Complete torque T. So complete torque T I have written here. But if I want to find out how much will be the torque resisted by this point, then I need to consider the shaft, the area, the material only up to that point from the center. So this much. So how much is going to be the torque resisted by this? Nothing but the torque resisted by inner core. We have already found out how much will be the torque resisted by the inner core. So this is what I have shown here. This diagram is a part of, is the inner core. the total torque diagram. It is only showing you Ti, because inner core having radius r by 2 is only resisting Ti. And obviously for this I can write this expression 16 Ti by pi d cube, or in terms of, okay wait, this is 2 Ti by pi r cube, right? I wrote 16 which comes here. Anyway, coming to the point that in this case I can use this expression for this shaft, for this inner core, like it's a standalone, it's a separate shaft, just like that. Earlier I was not knowing what is Ti, so I could not use it, right? Because total torque if I put, I will get wrong answer. How much will be the torque resisted by this, that I was not knowing. But since now I know this, if I put this value here, what I will be getting? 2. Ti is T divided by 16, right? And it is pi r cube divided by 8. If you simplify them, it will become 8, 8 and 8 will cancel, you will get T by pi r cube, which is the same expression as this one, which you get by finding out maximum value and dividing it with 2. So in this discussion, from this entire discussion, what did you learn? You learn that this expression is not restricted only for finding out maximum torque. You can use this expression to find out torque anywhere. So correct this concept. But to be able to do that, you should be knowing how much will be the torque resisted up to that point. To find out how much will be the torque resisted, you can use this expression. Integrate that to find out the torque resisted in any such core. And then you can put that value of torque here to find out the shear stress. Obviously, it is not the preferred way or easier way. Easier way is that find out the maximum value of torque and just, since the variation is linear, so divide it with 2, with 1 by 3, depending upon where is the point, right? I am not asking to use this method to find out the torque value. But if question comes regarding variation of torque, like the question that I have shown you, then this is the way in which you can solve the question to get the answer. And since you have understood it completely, there are many theoretical questions on torque variation that you can solve right now. And as I told you, I would recommend that you remember and note down this expression in your notes. When you are doing it, make sure to draw this diagram also, so that you will be knowing that for what situation, what parameters you have to apply. In exam, you can get confused, what is R, what is rho. You should be knowing R is a constant value here. Rho is a variable value which can vary from any inner value to outer value. So this is the learning from this whole discussion. Let's look at another example which will be different from this one, and let's master this concept further.